So guys, what was the last stuff that we talked about in the previous lecture? It was the discussion on one specific type of the differential equations, which were very easily solved, and the concept of the general solution, and then the concept of the particular solution, right? Now, over there, we solved an example. Here now, we're going to solve another one. So, we're solving example 6 of the second chapter. It says, determine which one of the following graphs shows the solution of the following initial value problem. As we learned in the previous lecture, the differential equation plus the initial condition is called the initial value problem. Now, in this specific example, our differential equation is this: dx over dy equal to 2x, and our initial condition is not given to us in a straightforward way. It says y is equal to 4 when x is equal to 1, right? Now, what does that mean? It means y at 1 is equal to 4, right? The meaning of this initial condition is this. Now, let us solve this initial value problem and then see the solution matches which one of these three graphs that is given to us. Okay? For this initial value problem, the differential equation, as we said, is dy over dx equal to 2x, and the initial condition is y at 1 equal to 4. Solution to the differential equation, or the solution without considering the initial condition, which, as we learned, is also called the general solution, is very easy to calculate. Dy over dx is equal to 2x. That means y is equal to the antiderivative of 2x, which as we know is equal to x2 plus c, right? So our general solution is y equal to x2 plus c, right? So, in order to determine this undetermined constant, what do we have to do? We have to use the initial condition, which was y at 1 equal to 4. If we do that, we're going to find out c to be equal to what? We're going to find out c to be equal to 3, right? So, if we replace this value of c into the general solution, we're going to get our particular solution, y equal to x2 plus 3, right? Now, which one of those graphs was for function y equal to x2 plus 3? It was this case B. Exactly, the second one, right? Very easy. Now, example 7 is also very easy, but it needs a little bit of your previous physical knowledge. It says we have the following information for the movement of a particle. Acceleration, which we have shown here with a is equal to t plus 1, and the particle's position at time 0 is equal to 2, and the particle's velocity at time 0, meaning at the start of the movement, is equal to minus 1. And it is required, we are required to find the position of the particle as a function of time for every t, right? Now, if you want to get a reminder of physics, position of a particle or a moving body at any moment is usually shown with s of t. The velocity is denoted with vt, and it is equal to the rate of change of position, meaning velocity is equal to d over dt of st or s prime t. And acceleration is denoted with at, and it is equal to the rate of change of velocity. So acceleration is equal to d over dt of v, and v is d over dt of s. So a is also equal to d2 over dt2 of s, or s double prime of t, right? Question. Now, what do we have to do in this specific case? First, we have to calculate the antiderivative for a, or acceleration, to find v. After finding v, we have to calculate its antiderivative again to find s, right? So we have v prime. Here we are writing what I just said. V prime is equal to the acceleration, and the problem tells us that the acceleration is equal to t plus 1. So v is equal to the antiderivative of t plus 1, which is 1 over 2 t2 plus t plus c, right? For this differential equation, this function that we have found, this solution that we have found, is the general solution because it has an undetermined constant which is denoted by c. Now, we can determine this undetermined constant by using one of the initial conditions that is given to us, and it is v at 0 equal to minus 1. If we use that initial condition, v at 0 equal to minus 1, if we put 0 into this equation, we're going to get 1 over 2, 0 to the 2 plus 0 plus c, which is equal to c, and it has to be equal to minus 1. So c has to be equal to minus 1. The undetermined constant that we had is now determined. So we can say that v of t is equal to this, 1 over 2 t to the 2 plus t minus 1. Said, I'm going to come back to you. Wait a little bit, please. So Now that V is determined, we are one step closer to finding S. Because S prime is equal to V, which is equal to this. Now, if we calculate the antiderivative for this function, we're going to reach to what? Antiderivative of t2 is t3 over 3. Antiderivative of t is 1 over 2 t to the 2. Antiderivative of minus 1 is minus t. And we have to consider the undetermined constant, right? Here, because we have a new undetermined constant, we have given it another name, C prime. You could have called it anything you want. Doesn't make a difference. Yes? Now, we have to determine.
Teacher, is this being recorded?
Yes, yes, absolutely.
Thank
No problem. Now, we have to determine this undetermined constant, C prime, using what? If you pay attention, there is another initial condition that we can put into use here. S at 0 equal to 2. Now, if we use that, S at 0 equal to 2, what is the result? We have to put 0 into this equation that we have for S. We're going to get 1 over 6, 0 to the 3 plus 1 over 2, 0 to the 2 minus 0 plus C prime equal to 2. And that equation simplifies to this, C prime equal to 2. So C prime is also determined and the function S is completely determined as a function of time. S of t, which is our solution, is equal to 1 over 6 t to the 3 plus 1 over 2 t to the 2 minus t plus 2, right? Now, guys, questions. Go ahead. Some of you had questions.
Teacher, at the last part,
Yes?
S of 2, S of 0 equals to 2.
Yes.
C prime equal to 2, right?
Yes.
Uh, the reason why it's equal to 2 was not because of that you wrote S of, I think, 0 equals to 2. So it's not always if S of 0 equals to 2, C of C prime will equal to 2, right?
No, it is not always the case. It depends on the specific case. Yes. For example, if S of t was 1 over, for example, 6, e to the t, right? E to the, for example, 1 over 6 e to the t plus c prime. Huh? What would happen over there? S at 0 would be 1 over 6 plus c prime, and that would be equal to 2. So c prime would be equal to 1 and 5 over 6, which is 11 over 6, right? So you see that c prime, or in general, the undetermined constant, is not necessarily equal to the value that the initial condition gives us at 0, right? Do you agree, Saeed?
Yeah,
It
yeah, teacher.
very well. So let's go let's go to the next example or subject. Now, guys, this subject that we have here is also very much familiar to you. You have all learned this in the high school.
Teacher.
What? What? Go ahead. So, guys, after our discussion on antiderivatives, our next subject of discussion is indefinite integrals, right? You are familiar with indefinite integrals from high school, right? Over there, you learned that these integrals in which the integral sign has no lower limit and upper limit is called the indefinite integral, right? Why do we call it the indefinite integral? Because the limits of integration are not defined. That is why we used to call it the indefinite integral. But now, having the knowledge of antiderivatives, we can have a more formal definition of indefinite integrals. And what is that? It is this. We define indefinite integrals as the collection of all antiderivatives of f as a function of x, right? So the collection of all antiderivatives for a function f is called the integral of f with respect to x and is denoted by this. The symbol, the elongated s, is called the integral sign. The function for which we are calculating the integral is called the integrand, and the variable of integration, which is shown with this dx, is called the variable of integration, right? Now, because we've learned how to write the most general antiderivative for a function f, now by knowing the definition of indefinite integrals, we can easily calculate the indefinite integrals for various functions. Here we have some very simple examples. For example, you know that the integration of 2x dx should be what? Should be the most general antiderivative for 2x, which is x2 plus c, right? Now, because you know that every antiderivative of 2x is gonna have this form, we can say that x2 plus c is the collection of all antiderivatives for 2x. Do you remember the theorem in the previous lecture? According to the theorem, if we found one random antiderivative for 2x, then that random antiderivative plus an undetermined constant would give us a family of functions for which, would give us a family of functions which includes every antiderivative for the function that we have in mind, right? So, the indefinite integral of 2x is x2 plus c. In the same way, the indefinite integral of x2 would be, according to the power rule, it would be x3 over c plus x3 over 3 plus c. The indefinite integral of sine of x would be minus cosine of x plus c. The indefinite integral of cosine of x would be sine of x plus c. The indefinite integral of e to the x would be e to the x plus c. Now, the indefinite integral of x to the n, where n is not equal to minus 1, according to the power rule that we had for antiderivatives, would be x to the n plus 1 over n plus 1 plus c. Now, in the process of calculating the indefinite integral for each of these functions, if you are unsure of the result of your integration, because the result is an antiderivative for the integrand, you can calculate the derivative for the result, and you can see whether or not it is equal to the integrand that you had in mind. Yes? Now, for the function x2 minus x plus 4, there is the indefinite integral we expect to be x3 over 3 minus x2 over 2 plus 4x plus c, right? Very easy. Now, let us have an example which is a little bit more complicated. Now, in example 8, it tells us in the following exercises, find the most general antiderivative or indefinite integral and check your answers by differentiation, right? Now, the indefinite integral of 1 over x2 minus 1 over 3 would be what? Before being able to write the antiderivative for the integrand, we try to do some simplifications. Instead of 1 over x2, we write x to the minus 2 so that we can use the power law, and we leave the rest as they are. Now, the indefinite integral of this integrand is equal to the sum of the antiderivatives of these components individually, right? Do you all agree? So the antiderivative for x to the minus 2, according to the power law, would be x to the minus 1 over minus 1. Now, minus the antiderivative for x2, which will be x to the 3 over 3, minus the antiderivative for 1 over 3, which is 1 over 3x. And you are not allowed to forget this undetermined constant, right? This is very, very, very important. If you forget to write this undetermined constant, it is a big mistake. Why? Because this undetermined constant is a very important part of the definition of indefinite integrals. Why? Because the definition says that the indefinite integral is the collection of all antiderivatives of the integrand. Right? Now, if you don't include this undetermined constant, then the function that you've written is not going to be the collection of all the antiderivatives for the integrand that you have. It is going to be just one of the antiderivatives it has, right? So it is very, very important, very, very important to not forget this undetermined constant. Okay, guys, go ahead.
Yeah, I think you have problem with your connection.
The audio quality has dropped, right?
So
Oh, okay. What about now? Did it get
it's
better?
now good.
Now good?
Yeah, yeah.
Oh, oh, okay.
Teacher, teacher, could you repeat that, please? We will see that on the record when you.
No, in the recording, I don't think you're gonna have a problem.
We won't have a problem.
In the recording, you won't have a problem. Yes. So, guys, do you see the screen? Very well. This was the result of our integration. After that, we just do some simplification, right? For the result to look better. X to the minus 1 over minus 1. Instead of it, we write minus 1 over x. And the rest is properly simplified. Now, the example also asks us to check our answers by differentiation. What does that mean? It means that we have to calculate the derivative for the result of the integration, and the derivative for the result should be equal to the integrand. So now let's see whether or not that is the case. Let's see whether or not it is true. Now, the derivative of the result of the integration, you have to calculate it, and you can easily see that it is going to be 1 over x2 minus x to the 2 minus 1 over 3. And as you see, this is your integrand, right? So the result of our integration is correct. Yes? It is very useful to do because the process of calculating the indefinite integral and definite integrals, it is very prone to mistakes, right? Especially when you have sine functions and stuff like that, it is very probable to make mistakes. It is very useful to check our answers by calculating a simple derivative. Now, case B. You're supposed to calculate the integral of t square root of t plus square root of t over t to the 2 dt, right? Now, the good way to do that is not to factorize square root of t in the numerator, but to write this in the form of a power function, also this in the form of a power function, then separate this fraction into two fractions, and then continue from there. If you do everything that I just said, you're going to see t to the 3 over 2 over t to the 2 plus t to the 1 over 2 over t to the 2. And if you do the simplification, you're going to reach to integration of t to the minus 1 over 2 plus t to the minus 3 over 2 dt. And you can calculate this integral very easily using the power law. And this is going to be the result of your integration. If you do the simplification on this result, you're going to reach to this. And you check the result of your integration by calculating its derivative. We see that the result of derivation of our solution to the integral is the same as the integrand. So we've done the integration correctly. Questions? I see chats. Oh, okay. Are we good? Alhamdulillah. Yes, that is always the problem. Now, for case C, we are supposed to calculate the indefinite integral of 1 minus cosine of 6t over 2. Now, according to that table for antiderivatives that we saw in the previous lecture, the logical thing to do here is to separate this chart into two charts, right? To separate this fraction into two entities. One of them 1 over 2, the other minus 1 over 2 cosine of 6t, right? Now, the integration for 1 over 2 is 1 over 2t. The integration for minus 1 over 2 cosine of 6t is minus 1 over 2 sine of 6t over 6. And at the end, we absolutely have to add this plus c. After doing some simplification, this would be the result of our integration. Now, we check the result by calculating its derivative. The derivative of t over 2 minus sine of 6t over 12 plus c is equal to 1 over 2 minus 1 over 2 cosine of 6t, which is the same as the integrand that we had. So it shows that the integration is done correctly. Again, case D, indefinite integral of 1 over 2 cosecant to the 2 x minus cosecant x cotangent x dx, right? Now, if you refer to the antiderivatives table that we saw in the previous lecture, the antiderivative for cosecant 2 is minus cotangent, right? An antiderivative for cosecant cotangent is minus cosecant, right? So if you use that table for antiderivatives, you're going to get this. And you have to check the result of the integration by calculating its derivative. The derivative of the result of the integration, as we see, is the same as the integrand. So we've made sure that the result we've got for the integral is correct. Now, case E. Indefinite integral of 1 minus cotangent 2. How do we do that? For cotangent 2, we didn't have anything in that antiderivatives table, right? So, we use a trick. We know that cotangent 2 of x is equal to cosecant 2 of x minus 1. If you don't know why that is true, it is very easy to show that. For cotangent 2, you can write cosine 2 over sine 2. Instead of cosine 2 in numerator, if you write 1 minus sine 2, then 1 minus sine 2 over sine 2 would be 1 over sine 2 minus 1, which is cosecant 2 minus 1. Right? Now, if you use this identity to solve this integral, what are you going to get? 1 minus cosecant 2 minus 1, which would be the integration of 2 minus cosecant 2. And for cosecant 2, we have something in that antiderivatives table, and it is minus cotangent, right? So the result of this integration would be 2x minus cotangent of x, which is plus cotangent of x, and don't forget the undetermined constant. If you calculate the derivative for the result, you see that it becomes equal to the integrand that you have. At home, when you're studying the lecture notes, it is absolutely necessary to go through the calculation process for all of these examples. Otherwise, your hand is not going to get ready to calculate integrals. Now, part F. Go ahead. Go ahead.
Just go up, please.
Which part?
The same part when you cosine square of x. This part.
It has names C, D, E, F. Which part? E?
I think it's yeah.
Oh, okay. Which part of it?
Cosine this part.
Yeah.
Cosine square of x.
It is equal to cosecant 2 of x minus 1. Yes.
We cannot do the antiderivative of cosine square of 2 because of that we have
Exactly.
right.
Completely correct. Exactly. So, for part F, the integrand in part F is a little bit more complicated. It is cosecant over cosecant minus sine. Huh? So we see that we don't have uh, any familiar identity to use here. So what is our solution? Our solution is to replace this cosecant with its value, which is 1 over sine, right? We use a definition of cosecant. So we replace cosecant in the integrand with 1 over sine in numerator and denominator. Yeah? Now, if we do some simplifications on this, what are we going to get? In numerator, we have 1 over sine. In denominator, we're going to use sine of theta as the common denominator. And we're going to have 1 minus sine times sine, which is 1 minus sine 2, right? Now, in this fraction, in this new integrand that we have, we can cancel out sine of theta with sine of theta, and we can write the result as 1 over 1 minus sine 2. We can further simplify this integrand that we found, because 1 minus sine 2 is equal to cosine 2, right? So, now we have to calculate the integral of 1 over cosine 2 of theta d theta, or the integral of secant 2 of theta. But we are lucky. For this one, we have an entry on that antiderivative table. The antiderivative of secant 2, the most general one, is tangent of theta plus c, right? That is the result of our integration. And in order to make sure that the calculations are correct, we calculate the derivative of the result with respect to which variable? With respect to theta, right? So you all see that if the variable of integration is a function of something, the result of the integration should also be a function of the same thing. So if the variable of integration, which appears in the integrand, and after d is x, then the result of the integration should be a function of x. If it is t, then the result is a function of t. If, just like in case f, the variable of integration is theta, then the result of the integration is going to be a function of theta, right? Now, you can check this on your own. Now, for part G, the integration of e to the minus x plus 4 to the x dx. Now, for this part, we are lucky and we have something in the antiderivatives table. The result of this, the integration of this part, is e to the minus x over minus 1. You remember that the antiderivative for e to the kx would be e to the kx over k plus c, right? Now, for this part also, we have an entry on that antiderivative table. The antiderivative for a to the x, as you remember, would be 1 over ln of a times a to the x. So the antiderivative for 4 to the x is 4 to the x over ln of 4. And never ever ever forget this plus c. After doing some minor simplifications, this is the result of our integration. And we can check whether or not our result is correct in this way. So, questions?
Teacher,
What? Go ahead, Ahmed.
in the part F, and I didn't understand it for the checking.
You didn't understand the checking? Yes.
Yeah, this part.
Very well. Oh, okay.
The rule,
No, you can do it. You can do it by the reverse of what we did here. Secant 2 is 1 over cosine 2. If you want to write in detail, you have to write this. You have to write secant 2 is 1 over cosine 2. 1 over cosine 2 is 1 over 1 minus sine 2. 1 over 1 minus sine 2 is equal to this, all of it. And this is equal to this, and this is equal to this, right? You have to go all of these steps that we took here in reverse. Yes?
okay, thank you.
You're welcome. So guys, now in example 9, we're gonna see for the first time in our lives one of the important applications of integration, right? Now, example 9 says solve the initial value problem in the following exercises. And in exercise A, we have dx over dy over dx equal to 3x to the minus 2 over 3, and this is our differential equation, and the initial condition that is given to us is this, right? Now, previously, in order to solve differential equations like this, we used to write dy over dx is equal to this, so y is equal to the antiderivative of 3 times x to the minus 2 over 3 plus c, and go on from there. But now that we know about indefinite integrals, we can find the solution in a more straightforward way. Look, please pay close attention. This is our differential equation, dy over dx equal to 3 times x to the minus 2 over 3. Yes? Now, here I can treat this differentiation dy over dx as a fraction. So I can treat this dy over dx as a chart in which the numerator is equal to dy and denominator is equal to dx. If I do that, I can write dy is equal to 3 times x to the minus 2 over 3 times dx, right? I'm going to be able to write this. Yes? Now, after writing dy equal to this times dx, we can integrate both sides of this equation. When dy is equal to this, the integration of dy also has to be equal to the integration of 3x to the minus 2 over 3 dx, right? So what have I done here? I've calculated the integration of both sides. Yeah? So, now look. Very good. Wait a minute, please. I'm going to come back to you. Okay? Now, I have this. the integration of dy is equal to the integration of 3 times x to the minus 2 over 3 dx, right? This is a very important conclusion. But let's actually calculate the result of this integration and that integration. The integration of dy is actually equal to what? It actually is the integration of 1 times dy, right? The integration of 1 times dy. Now, the antiderivative for y as a function of, the antiderivative for 1 as a function of y would be what? Y, exactly. Y plus a constant, right? But here we haven't written that constant. And I'm going to tell you why. Now, what about the result of this integration? Integration of 3 times x to the minus 2 over 3 dx. Yes, we can calculate it, and it is going to be this, right? So our conclusion here is that y plus a constant is equal to 9 times x to the 1 over 3 plus a constant, right? Why didn't I write the undetermined constant on the left-hand side of this equation? Because I could move it to the other side and combine it with the undetermined constant to the other side and give it a new name, right? So guys, as we were saying, the y in this side of this equation has an undetermined constant which we didn't write. And the reason why we didn't write it is that we can move it to the other side of the equation and combine it with this undetermined constant here, right? Now, overall, y equal to 9 times cubic root of x plus c is the general solution for this differential equation that we have here. Now, after finding the general solution, we have to take care of the value of this undetermined constant here. How do we do that? By making use of the initial condition, right? Now, look, if we consider our general solution and make use of this initial condition, we can say that minus 5 is equal to 9 times minus 1 to the 1 over 3 plus c. Minus 1 to the 1 over 3 is equal to what? Is equal to minus 1. So c is equal to 4. And we can say that our particular solution, in which we no longer have an undetermined constant, is this 9 times cubic root of x plus 4. Questions? Guys, I can hear you. I can hear you, and I'm receiving lots of noises. Okay? So, what about part B? In part B, we still have a differential equation, right? And now instead of one initial condition, we have two initial conditions. One of them tells us the value of the unknown function at 0, and the other one gives us the value of the derivative of the unknown function at 0. Although here we cannot say that y is equal to the antiderivative of 0, we can still solve this problem by taking the antiderivative two times, right? This thing that I said is better shown when we use the integral sign, right? Actually, here we need to do the integration two times to get to the general solution, right? Look and learn how we do that. Look, the differential equation tells us that d2y over dx2 is equal to 0. What does that mean? It means that d over dx of dy over dx is equal to 0, right? Now again, we treat this d over dx part as a caret, as a fraction. And we say that we can move this dx to the other side. So we can say d of d over dx is equal to 0 times dx, right? Now we know that 0 times dx is going to become 0, but we avoid writing that for the moment. Okay? Now, if we take the integral of both sides of this equation, we can write the integration of d of dy over dx is equal to the integration of 0 times dx. So, in the left-hand side of this equation, the variable of integration is equal to dy over dx, right? And the undefinite integral of 1 times d of something is going to become what? Is going to become that thing plus an undetermined constant. But we don't write the undetermined constant on the result of the integration of the left-hand side for the moment. And the reason for that is exactly the same thing as we said for case A. Now, this integral on the right-hand side of the equation, its result is what? The antiderivative for 0 is what? Is a constant, right? Now, you should notice that here we have given a name to this undetermined constant, C1. And you're going to see why we did that. Now, this equation is very familiar to us and very easy to solve. We can again say dy over dx is equal to c1, and we can treat this as a fraction and write dy is equal to c1 dx. Then we can take the integration of both sides of the equation to come up with this. The integral of dy is what? Y. And the integration of a constant is equal to what? That constant times x, or the variable of integration, plus another constant, right? So we reached to this conclusion: y equal to c1x plus c2. So the unknown function is determined now, and this y equal to c1x plus c2 is the general solution to this differential equation. Notice one thing that is very important here. The order of differentiation of y with respect to x here is equal to what? It is equal to 2. What is the number of undetermined constants that we have in our general solution? It is also 2, right? So, I'm going to give you a generalization here. If the Muslim, please mute your audio. I'm just hearing your brother's voice. Uh, Unfortunate.
مسلم كاتناش نكيلرا
نعم يا مسلم
Guys, please quiet. No problem. So,
Hey, no problem, Muslim.
okay, no problem. So, in general, if the highest derivative that we have in the differential equation is a derivative of order n, then in the general solution for that differential equation, we're going to have n undetermined constants. So if this was of order 3, in the general solution we would have 3 undetermined constants. If this was of order 4, in general solution we would have 4 undetermined constants. Okay? That is an important point to have in mind. Now, the general solution is found, and we can easily use these initial conditions to find the value of C1 and C2 and determine the particular solution, right? But before we go through that, let us find a way to use the integration to solve a differential equation faster. So, as we said here, the process above for solving simple initial value problems is a very important process, and you'll be using it throughout your engineering life. the process is presented to you in a very detail, in every detail, so that you understand what is going on. That being said, you can do some of the steps in your head and write a summarized version of the process. If we write the process in a summarized way, what can we what is it that we're going to write? This is our differential equation. If we integrate both sides of it, the integration of second derivative is what? Is the first derivative, right? The old saying that integration and derivation have a reverse effect. That is somehow true, but not a very accurate statement. Now, the integration of the second derivative becomes the first derivative. The integration of 0 is a constant, right? Now, for this equation, we again calculate the integral for both sides. The integration of dy over dx is y. The integration of c1 is c1x plus c2, right? This is a summarized way of writing the steps when we are using the integration to solve our simple differential equations. Now, after finding the general solution, as we said, we have to use the initial conditions to find the value of these undetermined constants. Now, because we have two undetermined constants, we also need exactly two initial conditions to determine all the undetermined constants. And we are lucky and we have the two initial conditions that we need. The first one said the derivative of y at 0 is equal to 2. So this is y, its derivative with respect to x is c1. That means c1 is equal to 2. The other initial condition said that the value of y at 0 is equal to 0. Y is equal to this. The value of y at 0 is c2. So c2 is equal to 0, right? Wait. So we can say that y is equal to what? It is equal to 2 times x. And that is our particular solution, right? Now, as we said, if the differential equation that we have is of order n, meaning the value of the highest derivative in it, is of order n. So, sorry. If the differential equation that we have is of degree n, meaning the order of the highest derivative that there is in it is equal to n, that has two implications. The first one is that in the general solution for that differential equation, we're going to have n undetermined constants. The second implication is that in order to reach to the particular solution, we're going to need at least, or no, not at least, exactly n initial conditions. In this example, the differential equation that we had was of order 2. So the general solution had 2 undetermined constants, and we needed 2 initial conditions to solve it. Right? Now, in the next example, you see that the differential equation that you have is a 4th degree differential equation. In order to solve it, you need 4 initial conditions. And you know, just by looking at the differential equation, that the general solution to this differential equation is going to have 4 undetermined constants. So, guys, you had a question. Go ahead and ask your question. Do you hear me? Yes.
In this question,
Yeah?
we need just say we need two times antiderivative, yes?
Yes, exactly.
And we can say that just the antiderivative of 0 is equal to c,
Yes.
and y prime of 0 is equal to 2, it means c1 is equal to 2. Can't we use this?
Actually not. Because in this specific problem, that is true. But I can give you 1,000 problems in which that thing that you just said is not going to happen. For example, imagine you had d2y over dx2 equal to sine of x plus x2 plus 1, for example. It depends on the specific function that you're working with. The process that is introduced to you here is the process that you have to take. And this process is going to work for every problem in which on one side you have the derivatives of the unknown function, and on the other side you have a function of the variable that the unknown function depends on. Okay? So what is important here is the process. The problem itself is simple. You need to learn the process in order to be able to solve more difficult problems, not just that. Okay, Abbas? Very good. So the process is absolutely important here. Go ahead.
When you said that y prime y prime 0 is equal to 2, it means y prime is any value of x is equal to 2.
Sorry, I didn't. I got distracted. Can you repeat your question, please?
When you said that y prime 0 is equal to 2,
Yes.
it means y prime of any value of x is equal to 2.
No, 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 no,
y
no.
prime,
No.
y prime 1 is equal to 2, y prime is equal to 2.
For this specific problem, for which y is equal to c1x plus c2, y prime is equal to c1, right? And that is a constant. Yeah? So we had y prime at 0 equal to 2. From that, we concluded that C1 is equal to 2, right? But even if I gave you y prime at 1 is equal to 2, still you would conclude that C1 is equal to 2. Because the value of y prime is constant and it doesn't depend on x. But if the function y was not a function like this, for example, if y was a function like c1 x2 plus c2x plus c3, you see that in that case the value of y prime would depend on x, and you couldn't say that for dimension case. Yes? Good. Any other question?
This y prime is equal to C1, yes?
Yes, exactly. Y prime for this function y is equal to c1. Yes.
And if y prime 0 is equal to 2, it means C1 is equal to 2.
Yes. Because y prime at
So,
0 is equal to c1.
so can't we say that y prime of any value of x is equal to 2?
I told you yes, but that is not an important point, because that is true only for this problem. Oh, keep that in mind. That is not something that can be generalized. For this problem, yes. Okay. So, part C. What do we have here? What we have is this. C is equal to, sorry, the differential equation that we have here is d4y over dt4 is equal to minus sine of t plus cosine of t, right? And because the derivative here is of order 4, in order to find the particular solution, we're going to need 4 initial conditions. Here we have 4 initial conditions. Y at 0 equal to 0, y prime and y double prime at 0 is equal to r equal to minus 1, and y triple prime at 0 is equal to 7. Now, just like any other differential equation, I'm hearing motorcycles. Good. At Where are you guys? Where are you? Motorcycles? Ismail, is that you? Okay. So, just like any other differential equation, we first have to find the general solution. After finding the general solution, we use the initial conditions to find the value of the undetermined constants in the general solution. When we do that, the particular solution is found. Yes? Now, the process of finding the general solution for this differential equation is very routine. We say that d4y over dt4 is equal to minus sine of t plus cosine of t. If we take integration from both sides of this, the integration of the left-hand side is going to become d3y over dt3. The integration of the right-hand side is going to become cosine of t plus sine of t plus c1. Okay, we give a name to this undetermined constant because we know we're going to have more of them. Now, we take the integration of this side and equate it to the integration of the other side. And we're going to reach to this d2y over dt2. Integration of cosine plus sine plus c1 is sine minus cosine plus c1t plus c2. Right? There's still work to do. We have to take the integration again. The integration of the left-hand side of this is going to become dy over dt. The integration of the right-hand side of this is going to become minus cosine minus sine plus what? The integration of c1t is 1 over 2 c1t to the 2 plus c2t plus c3, right? Now, unfortunately, there is still some work to do. We have to integrate this once again to find y. The integration of the left-hand side becomes y. The integration of the right-hand side is minus sine plus cosine plus 1 over 6 c1 t to the 3 plus 1 over 2 c2 t to the 2 plus c3t plus c4, and this is our general solution, y equal to this is the general solution that we found. You see, in this general solution, wait, in this general solution, we have 4 undetermined constants as we expected. Now we have to determine the value of these 4 undetermined constants, C1 to C4, using the initial conditions to reach to the particular solution. Go ahead, Said, go ahead. Guys, somebody had a question. So guys, we were at the point that we needed to use the initial conditions to determine the value of these undetermined constants in the general solution, meaning C1 to C4. Now, using one of the initial conditions, y triple prime at 0 equal to 7, the value for y triple prime is found here. It was equal to cosine of t plus sine of t plus c1. If we put in 0 here, cosine of 0 is 1, sine of 0 is 0. So 1 plus c1 is equal to 7. That means c1 is equal to 6. The second initial condition told us that y double prime at 0 is equal to minus 1. Y double prime at 0, if we want to evaluate it, y double prime was equal to sine of t minus cosine of t plus c1t plus c2. Now, if you put in 0 in it, we're going to have minus 1 plus c2 equal to minus 1, which gives you c2 equal to 2. The third initial condition, y prime at 0 equal to what? Equal to 0. Y prime was found out to be equal to this. If we put in 0 instead of t into this equation, we're going to have C3 minus 1 equal to minus 1, which is going to give you C3 equal to 0. And the fourth initial condition, which told you that y at 0 is equal to 0. Now, y was equal to this. If you put in 0 in it, what are you going to get? You're going to get 1 plus C4 equal to 0. That means C4 is equal to minus 1. Now we have determined all the undetermined constants. If we replace these values for C1, C2, C3, and C4 into this equation, which was the general solution, we're going to find this, which is our particular solution, right? Minus sine of t plus cosine of t plus t to the 3 minus 1. Now, guys, this is exercise 1. You have to solve it till next week. It has some questions, 35 here, 20 here. There's a number of very easy questions. You have to solve them all. Write it down on a paper and take pictures of the paper. Turn it into a PDF file. Write your name on the PDF file and send it to me. Okay?
Okay, teacher.
And when you want to do that, when you want to do that, there is an application, a cell phone application, which is going to help you a lot. Let me show it to you. There's an application called CamScanner. Let me find this application for you. What?
About other exercise that we have in note 5, that we should calculate it.
Oh, there are other exercises over there too, right?
Yes, right.
Uh-oh. So guys,